So, if you've ever found yourself deep in the world of statistics, you've probably hit this exact crossroads. Should I use a one-tailed or two-tailed test? It sounds like a small detail, but it's a choice that can totally change your results. Let's break down what this really means and why getting it right is so important. Okay, imagine this. You switch up your study routine and bam, your test score goes up. Awesome, right? But here's the million-dollar question. Did your new method actually cause that improvement? Or, did you just get lucky? This is the exact kind of puzzle statistics is designed to solve. So here's our game plan. We're going to start with that big question. Is it real or is it random? Then we'll grab our basic toolkit, which is all about hypotheses. After that, we'll dive into the two big players, the focused bet of the one-tailed test and the safer bet of the two-tailed. Then we'll see why this choice is such a massive deal, and we'll finish with the one golden rule you absolutely have to remember. All right, let's jump right in with that fundamental idea. How in the world do we separate a real, meaningful effect from just, random noise? This is really the question at the heart of so much research, and the statistical tool we use to get a clear mathematical answer is called a t-test. It's designed specifically to figure out if the difference we're seeing between groups is actually significant or if it's something that could have just happened by pure chance. Okay, but before we can even think about running a t-test, we need a solid framework. And that framework is hypothesis testing. It's all about setting up two competing claims before we even lay eyes on our data. On one side, you've got the null hypothesis, or H0. Just think of this as the ultimate skeptic, the status quo position. It basically says, nope, nothing interesting is happening here. Any difference you think you see is just random luck. Then, on the other side, you have the alternative hypothesis, H1. This is your big idea, the exciting claim you're hoping to prove, that there is a real effect. Our entire goal is to see if we have enough evidence to reject that boring null hypothesis and embrace our new alternative. Now let's get to the main event. First up, the one-tailed test. The best way to think about this is like you're a gambler making a very specific, very focused bet. You're not just saying things will be different. You're confidently predicting the exact direction of that difference. You're calling your shot. Now, this is a more powerful kind of test. But you know what they say? With great power comes great responsibility. You can't just use it whenever you feel like it. So, what are the actual rules for placing this kind of focused statistical bet? Yeah, the conditions for using a one-tailed test are incredibly strict. You can only use it if you have a rock-solid theoretical reason to expect an effect in one and only one specific direction. This means an effect in the opposite direction has to be either completely meaningless or literally impossible. And here's the most important part. You have to make this decision before you see a single data point. This example makes it super clear. Imagine a company develops a new fertilizer. The only outcome they care about is an increase in crop yield. If the yield stays the same or even goes down, the product is a failure. They aren't interested in proving it's worse, they just won't launch it. Their interest is purely one-directional. And this is how we'd write that out. We're testing if the new mean yield, represented by that Greek letter mu, is greater than the old yield of 20 tons. That greater than sign is the key. It's what makes it a one-tailed directional test. Now let's flip the coin and look at the other option, the two-tailed test. This is the more common, more conservative, and generally the default choice. Think of it as the safer bet. A two-tailed test doesn't try to predict a direction. It just asks, hey, is there a difference here at all? It's way more exploratory and open-minded. So when is this the right approach? Well, you use a two-tailed test whenever you're open to an effect in either direction. Is a new teaching method different? Maybe it's better, maybe it's worse. You want to know either way. Because it doesn't try to guess the outcome, it's considered a more conservative and scientifically rigorous approach in most situations. Consider this. A company claims its batteries last for 10 hours. You're a consumer watchdog group, and you want to test that claim. You'd be just as interested if they lasted significantly less than 10 hours as you would if they lasted significantly more. Any deviation from their marketing claim is important news. And notice the difference in the notation here. The alternative hypothesis now uses a not equal to sign. That symbol tells you we're looking for a difference in either direction, higher or lower. We're keeping our options open and checking both tails of the distribution. Okay, so we have the focused bet and we have the safer bet. Why does this choice matter so much? Because as we're about to see, it can completely change your conclusion, even when you're working with the exact same data. So let's imagine a company creates a new energy drink and they claim it reduces your reaction time. They test it on a group of students, they run the numbers, and the results? Well, they depend entirely on which test they chose to use from the start. Now, watch this. If the researchers decided beforehand to use a one-tailed test because they were only interested in a faster reaction time, they'd get a p-value of 0.015. Looks significant. But if they had used the more scientifically rigorous two-tailed test, the p-value would be 0.03. See how the p-value is exactly doubled? With the same data, the one-tailed test gives a much stronger-looking result. This shows how it's easier to find significance with a one-tailed test, and that creates a pretty dangerous temptation. This table sums up the trade-off perfectly. A one-tailed test gives you more statistical power to find an effect you predicted, but its risk is huge. It is completely blind to a surprising effect in the opposite direction. The two-tailed test is more honest. It's open to any outcome, but it requires a stronger effect, a bigger signal to be considered statistically significant. And that temptation leads to a really serious problem in science called p-hacking. Here's how it happens. A researcher runs the correct two-tailed test, but the result is a letdown. Say a p-value of 0.06, just missing that sweet significance level. They're disappointed. Then they notice that the data was trending in the direction they wanted, so they go back and rerun the analysis, but this time as a one-tailed test. Suddenly, their p-value is 0.03, and they can claim success. This isn't science. It's just manipulating the process to get the outcome you want. Which brings us to our final and, frankly, most important section, the golden rule for making this choice the right way. This is it. This is the single most important takeaway from all of this. The decision to use a one- or two-tailed test must be based on your theory and your research question before the experiment even begins. Letting the data guide your choice after the fact isn't just bad practice, it's cheating. And that's the fundamental choice I'll leave you with. When you design your own research, what are you going to prioritize? The statistical power to find a specific result you're hoping for, or the scientific honesty to find the true one, whatever it might be? The choice is yours.